We defined impulse as the change in momentum experienced by an object. Now, you remember what two things were required for there to be an impulse or a change in momentum experienced by an object? Kyle, what do you got to do to an object in order to change its momentum? You got to what? You got to apply a force, right? You're not going to increase or decrease the velocity of an object and therefore change the momentum of an object without applying a force on it. So impulse certainly requires a force. Now, the more force you apply, the bigger the impulse that the object is going to experience, the bigger the change in momentum that it's going to experience, right? What else affects it? The time. The more time you apply the force for, then the more impulse the object experiences as well, or the more the momentum increases or decreases as well. Now, impulse is also equal to m times v. Now, momentum is m times v, right? If momentum is m times v, then change in momentum is m times delta v, right? Don't forget that. Okay, if you write it as m times v, then it's quite likely at some point you're going to make a mistake as a result of that. Momentum is mv, impulse is m times delta v. Now, this is the form of the equation that appears on your data sheet. F times delta t is equal to m times delta v. But we add this delta p, or this impulse symbol, as well. Three parts to this equation, two of which appear on your data sheet, one of which doesn't. Remember that you're always going to use two of those three parts. So you could use delta p is equal to f times t, or delta p is equal to m times delta v, or you could use f times t is equal to m times delta v. Whatever two parts of the three that work for you with the givens that you have. Make sense? All right, what are the units that we use for impulse? Sorry. What units do we use? There's two sets. Kyle, what's one of them? Newtons times seconds, and that comes from the F times delta t equation, right? Newtons seconds, absolutely. What's the other set of units that we use for impulse? Right, and that comes from the m times delta v part of the equation. A Newton second ends up being exactly equal to a kilogram meters per second, so it doesn't matter which one you use. But recognize both, because sometimes on a test or a quiz or an assignment, you'll see Newton seconds. Sometimes you'll see a kilogram meters per second, and you have to know what each of those units represents. So if you answer a question, use whatever you want. Okay, but if you're looking at a test, sometimes they specify it, so just make sure that you understand that both of them end up being the same thing. And finally, the last question that I want to ask you here is momentum, or at least for now, with regards to this equation at least, is momentum, or impulse, I should say, a vector or a scalar? It's a vector. Yeah, it's a vector. And along with that, knowing that it's a vector quantity, we know that it could be a positive value or a negative value. Now, impulse is going to be a positive value if the momentum increases in the positive direction. So if you're moving to the right and the momentum increases to the right, that's a positive impulse. But on the other hand, if you're moving to the right and the momentum decreases, that's going to be a negative impulse. If you're moving to the left, or the negative direction, downwards, south, left, an increase in momentum in the negative direction will be a negative impulse, and a decrease in momentum in the negative direction will be a positive impulse, because it requires an upward force, or a positive force in order to do that, right? You got an object moving downwards, it hits the ground. When it hits the ground, it loses momentum, right? Right? It's a loss of momentum in the negative direction. Well, what kind of force is required to do that? An upward force. The ground has to push upward, and therefore it has to be an upward impulse. Make sense? Okay, finally, there is one more question that I forgot I was going to ask you here. If you're dealing with two objects, most of the questions, to be honest, that we deal with impulse aren't involving two objects. Well, I mean, in the end, a lot of them are, but a lot of times you're only given information about one object. Okay, if I push an object to slow it down, most times you're given information about the object that I'm pushing, not about me. But in the end, if you are given information about both objects, what do you got to remember to do? Yep. Yeah. Fully analyze one. Now, you may, in the process of completing a problem, analyze both, but you got to make sure that you do them separately. Like it's two completely separate problems. Okay, if car 1 pushes on car 2, that's great. Analyze either car 1 or car 2. And then you may turn around and do the other one after you finish the first one, but not at the same time as you're doing the first one. Right? Analyze one or the other. Now, what's the other thing that we talked about with two objects? The other thing that you can remember?
Well, if you've got car 1 and car 2, you might not have all the information you need to solve the problem of, well, let's say car 2.
Yep.
But car 1 can give you the necessary information to solve for what you need for car 2.
Perfect. So if you have information about two vehicles or two objects colliding with each other, you know that the impulse experienced by one is equal and opposite to the impulse experienced by the other. So it is conceivable two cars, or let's say a car and a truck collide. You know lots about the car. Well, that allows you to find the impulse experienced by the car. You know, by extension, the impulse experienced by the truck, which may help you to find something involving the truck. Does that make sense? The impulses are equal and opposite. What else is equal and opposite when two things collide, hit each other, besides the impulse? The force, right? That's Newton's third law, the forces being equal and opposite. All right? We're going to take a look at worksheet number 2 now, specifically questions 6, 7, and 8 on worksheet number 2. Number 6 says a 1.00 kilogram ball traveling towards a soccer player at a velocity of 5 meters per second rebounds off the soccer player's foot with a velocity of 8.5 meters per second. I'm going to pull out the red pen here and identify something that could lead to a silly mistake. It doesn't tell me right, left here. It doesn't tell me up, down, north, south. But it does tell me that the ball is moving towards the soccer player and then it rebounds, so it's moving away. Right? And I got to be careful there that something is positive and something is negative, right? Now, we don't have like a standard for defining positive and negative there, like we do with right and left, up and down. You know, up is positive, down is negative, right? But when it's coming towards me or away from me, what's positive, what's negative? Whatever you want. Okay, whatever you want. Let's say as it's coming towards, let's say that's positive. If it's going away, let's say that's negative. But you could absolutely do it the other way around, and that would be absolutely fine. Okay? Now, it tells me the time of contact here is 2 times 10 to the negative 2 seconds. What's the magnitude of the force that the foot applies on the ball? So let's write down some givens here. We're going to say that the mass of this is 1.00 kilograms. By the way, this is an impulse question, right? How do we know that? Before we even write down our givens, how do we know that this is an impulse question? Yep. Yeah, it involves force, and it involves time. So right away we're thinking impulse. Right? Just like when we see a funny angle, we right away think, I don't like funny angles. Okay, when we see force and time, we right away think impulse. Okay, so we have the mass, we have VI. VI we're going to make positive 5.00 meters per second. And we have VF, we're going to make it negative 8.50 meters per second. You could have made it the other way around, negative 5 and positive 8.50. Doesn't really matter. The time of contact is 2 times 10 to the negative 2 seconds. And we want to find the magnitude of the force. You know what, we'll find the force, and then if it works out to be negative, well, then that's okay, because the magnitude is just the absolute value of that, right? The positive version of that. All right, it's an impulse question. You told me that already. There's 3 parts to the equation, delta P, F times T, M times delta V. Which 2 parts do you want to use for this? Which 2 parts do you want to use for this? Okay, so delta P is equal to M times delta V. All right. Delta P is equal to M times delta V. M is 1 kilogram. Delta V is VF minus VI, or negative 8.5 minus 5. So what is that? Negative 13.5. Yeah, negative 13.5 Newton seconds. Good. There's the impulse. But that's not what I'm looking for, right? So what next? What am I going to do now? Yeah. Delta P is equal to F times T. Let's rearrange that to solve for F. Delta P is negative 13.5. I am going to get a negative value for force here. That's okay. I can just drop the negative to get the magnitude. My time here is 2.00 times 10 to the negative 2. And that gives me a force, what was it, 675 did I say? Yeah, negative 675, which we're going to take the absolute value of, and we end up getting 675 newtons. Now, that's not actually quite the way that I did it myself. Okay, when I did it, I set F times T equal to M times delta V right off the top. Do you see how that's really the same thing? It's one step instead of two. It doesn't really save any time. It's just the way that I do it. Okay, it's no better, no worse. You use two parts of the equation. I use these two parts right away. Okay, when we solve this question here today with you, we use these two parts and then these two parts. That's fine. Doesn't really matter. Okay, how many people did it more my way, my first way? Okay, how many people did it this way? Okay, whatever. They're both valid. Okay, 7. Says a 1.5 kilogram rock falls from rest from the top of a 10-meter high building and strikes the ground below. What's the impulse experienced by the rock during its fall? What happens to this rock as it falls? Yeah, good. It accelerates. It speeds up at negative 9.81 meters per second squared. So this is going to gain momentum, right? It's going to gain momentum in the negative direction, which means the impulse here should be negative, right? Because it's gaining momentum in the negative direction. All right, we're looking for impulse, so it doesn't take a genius to figure out that we're going to use impulse for this question, since it asks for impulse. All right, what do we got here? We got a mass of 1.50 kilograms. We've got a VI of 0, because it says it starts from rest. I'm going to say my displacement is negative 10 meters because it's downwards, right? Ends up below where it started. We want to find the impulse. So let's say impulse is equal to, I don't know F and I don't know T, so I'm probably going to use this, although I don't know what delta V is either. I could find it. Well, I know what VI is, so let's find VF over here. How am I going to do that? How am I going to find VF? Cal? Yeah, VF squared is equal to VI squared plus 2AD. Now, VI is 0. We got lucky there. If it's not 0, be careful that you sub a number in, although if it's upward, downward, it doesn't really matter because VI is speed, which is a scalar. So we just sub in the value of it, right? Not the sign of it. But A is a vector, we need the negative there. So is displacement is a vector, we need the number there. Solve for VF there, and it works out to be 14.00714 meters per second. That's the final, what have I just solved for? The final speed, the final velocity would be negative 14, right? And that's where we end up getting the negative value for delta P. I said Newton seconds for that, but you could have said kilograms meters per second as well. And again, it is a negative value because, well, mathematically, because this VF for final velocity should be negative. But conceptually, it should be negative because we're gaining momentum in the downward or the negative direction. Now, number 8 says it's the same scenario here, except this time we want to find the force of the ground acting on the rock that causes it to stop. After it's fallen, the rock stops. If the impulse experienced by this rock during its fall was negative 21, then how much momentum did it have the moment that it struck the ground? How much did it have before the rock was dropped? 0. So how much does it have as it strikes the ground. Not after it struck the ground, but as it strikes the ground. No? Not. Negative 21. It gained 21 in the downward direction, right? So we're going to say the impulse experienced by this rock when it hits the ground is what? Positive 21, because it had negative 21 when it struck, then it had 0 after it stopped, and 0 minus negative 21.0 equals 21. Does that make sense? I mean, think about that logically, right? What just happened? We lost momentum as it struck the ground. We lost momentum in the downward negative direction. That means the impulse is positive. So it is a positive 21 here. Now I'm just going to say delta P is equal to F times T. Rearrange that to solve for F. I get delta P over T. Delta P is a positive 21.0. And delta T is 0.350 seconds, which gives me a force of positive 60.0 newtons, which if we think about it, and we always want to be thinking about this, right? Like not just getting a number, but always thinking about, does it seem right? Because if it doesn't seem right, that helps us sometimes to catch mistakes, right? If we're not thinking about it, we just blindly write down the answer we get, then sometimes we end up making a mistake as a result of that. If we think about this, it should be a positive force, right? Because if something's stopping as it's moving down, what do we got to do? Push up on it, right? And that's it. The ground is pushing up on it. Right?